The last couple lessons we've done on kinetic energy and potential energy and how to calculate them have really been building up to this one. Knowing about kinetic energy and knowing about potential energy really isn't that useful on its own. What is a really powerful tool in physics is the law of conservation of energy. And in order to be able to use this law, we need those tools from earlier on how to calculate kinetic energy and how to calculate potential energy. So before I talk about this conservation law, I'll remind you, I mentioned this a couple of lessons ago, that there's a short list of things in our universe that are conserved, things where the amount of them never changes. And I mentioned before, a couple of things on that list are things you likely would have talked about in a chemistry course. So electric charge and mass are two things that are conserved in our universe. And you would have used knowledge of the conservation of mass, for example, if you've ever balanced a chemical equation. But in addition to electric charge and mass, there's a few other things that are also conserved in our universe, where the amount of them in the universe never changes. One of them is energy, and it's probably one of the biggest ones, and we're going to use that a lot in physics. Another one is momentum, which we'll use in a later part of this course or of another course. And then there's a few more things. So energy is one of a few things in our universe that is conserved. The way we often state this is by saying that energy cannot be created or destroyed, only transferred from one form to another or from one object to another. So a lot of the time people see an object that has some energy, and then a little while later they look at that object and maybe it appears to have less energy. Maybe at the beginning the object was going fast and now it's going slower. And they say, it has less kinetic energy. That energy must have disappeared. Or maybe the object used to be high up and now it's lower down. And people say, it has less potential energy. That energy must have disappeared or been destroyed. But what this law tells us is that can never happen. That energy that the object lost when it slowed down or when it got lower didn't go to nowhere. It didn't get destroyed. It must have gone somewhere else. Either it got transferred to another form. So maybe as the object fell down, it gained some speed. It went faster and faster. So it lost potential energy, but gained kinetic. That's an example of energy going to another form. Or the energy might get transferred to another object. So maybe that object falls down and then it hits the ground. And now that energy that it had is now in the ground, probably being converted to thermal energy or something like that. So energy, despite what it may seem sometimes, energy never disappears and it never comes out of nowhere. It only gets kind of shifted around between different forms and between different objects. Now, what we're most interested in looking at in this course is single objects. So looking at one object at a time. What is the energy in that object doing? What forms is it in? Is it coming in from other objects? Is it going away to other objects? And a good formula that sort of takes the essence of the conservation of energy law and lets us apply it to a single object is this. So to break this down, this says that object will have some kinetic energy initial, some potential energy initial. Then there's something to do with some work over here. We'll talk about this term later. And then later on, at final, it'll also have some kinetic energy maybe and some potential energy maybe. So basically what this equation does is it takes all the types of energy that exist in the object at the beginning and adds them together. And it says that has to equal all the energy the object has at the end because energy is conserved. Where this work term comes in, that's any energy the object might have gained from another object. So new energy that was brought in. Or this could be a negative number, in which case it would be energy that left this object and went to a different object. So here's all the energy the object had at the beginning. Here's all the energy the object has at the end. This is any new energy that was brought in or sent out from or to elsewhere. And all of this together basically makes sure that this object has the right amount of energy to start with and to finish with. That energy is conserved. So I want to talk a little bit more about this word other that I put in here. What other refers to is forces we don't have a type of potential energy for. For example, you know that gravity can do work, but we have a special way of accounting for work done by gravity, right? Remember when we talked about gravitational potential energy? We said that gravitational potential energy was the amount of work that gravity had the potential to do. So work done by gravity is already accounted for in our potential energy. There's also formulas for potential energy of springs, for example. So if work is done by a spring force, well, we have a formula that calculates the potential energy of a spring. So we don't need to include in this other part, we don't need to include work that's done by forces if we already have a type of potential energy that goes with that force. So work done by gravity, we don't include it because we have gravitational potential energy. Work done by springs, we don't include it because we have spring potential energy. Work done by friction, we would include here because there's no type of friction potential energy. Work done by tension, we would include here because there's no type of tension potential energy. And in Physics 11, in this course, really we're just going to be working with gravity and a couple of other forces. So pretty much this is going to be, for our course, work done by things other than gravity, because gravity is really the main type of potential energy that we talk about. So this whole term then represents energy that's transferred to or from another object. So to recap, my object has some kinetic energy, maybe, and some potential energy, maybe at the beginning. Energy comes in, perhaps, from another object in the form of work. And then at the end of all this, my object will have some energy at the end, maybe in the form of kinetic, maybe in the form of potential. This equation might seem a little mysterious right now, but when we do an example and we start using it, it'll hopefully become a little bit more clear. Now, where this equation is particularly useful is when this work term is 0. And that is maybe not surprising. I think if any of you are a little confused at this point in the video, it's probably because you're not quite sure what this work other thing is all about. So you'll be happy to know that most of the time when we use this equation, this is 0. And the equation becomes much, much simpler. So if we know that we like to use this equation when work other is 0, let's look at some situations where work other is or could be 0. First one I want to look at is a roller coaster going down a hill. So let's do a sort of a cheater free body diagram. I'm not going to draw just the object, just the coaster without the track and without the people in it. I'm just going to do a sort of a sketch free body diagram over top of this image we have already. There's going to be gravity pulling down on the roller coaster, and there's going to be a normal force that is perpendicular to the track, to the surface the roller coaster is touching. Here's the interface between the roller coaster and the track, and the normal force is perpendicular. So gravity is Fg, and this guy up here is going to be Fn. But notice that Fn will do no work. The reason for that is, well, the roller coaster is moving this way along the track. But Fn is perpendicular to the track. And you might recall that work is force times distance, but they have to be parallel. So because the motion or the distance of the roller coaster is one way, but this force is perpendicular to that, this does not do any work. Gravity will do work on the roller coaster because it's not perpendicular to the direction the roller coaster is moving. So if I were to then apply our equation up here to this roller coaster situation, I'm asking, is work other 0? Is there any work being done by forces that we don't have a type of potential energy for? Well, there's no work being done by this force. There's work being done by this, but this is gravity. We have a type of potential energy for that. So there is no work being done by forces other than gravity, which we have a potential energy for. Therefore, the work other is 0. Next example, a pendulum swinging back and forth. Okay, so here's a ceiling. I got a string tied to it, a heavy mass on the string, and it's kind of swinging left, right, left, right. Free body diagram. Gravity is pulling down, and tension is pulling along the rope here on the object. Again, gravity is Fg, and that tension force, similar to the normal force over here, it does no work. When the pendulum is moving kind of in this direction, as it is right now, the tension is perpendicular to the motion. If the pendulum were down here, moving kind of left-right as it goes through its lowest point, then the string would be directly above it and tension would be up. Again, perpendicular to that motion. So no matter where the pendulum is, tension is perpendicular to its motion. Therefore, it can't do any work. So the only force here that could do work is gravity, but we have a type of potential energy associated with gravity. So we don't count it in that work other term. So work other here is also going to be 0. Okay, let's change things up a bit. Do some slightly different examples. A car is getting to a stop. There's my car. And all the wheels are locked. It's leaving some skid marks behind it on the front wheels and the back wheels there. And my free body diagram is going to look like this. I got gravity going down. I've got normal force going up. And I've got friction pushing backwards. Now, in this case, the normal force does no work because the car is moving right and the normal force is perpendicular to that. Also, I didn't write it here, but gravity also does no work in this situation. Again, the motion is this way to the right, and gravity is perpendicular to that. So there's no work done by gravity either here. Force friction, however, will do work because the car is moving right and friction's going left. Those are parallel, so work is done. And in fact, you might say they're anti-parallel. So friction is doing negative work. It's taking energy away from the car and converting it into heat. So here we do have a force other than gravity, a force that we don't have a type of potential energy for, and that force is doing work. So that would be a great example of work other. Friction is doing some other work. So my work other is not equal to 0 in this case. A ball flying through the air with air resistance. Quick cheater free body diagram. Gravity going down as the ball flies kind of up and to the right. Air resistance is going to be opposing that instead of going down and to the left. You can think of this as like the wind blowing on the ball. Now, gravity can do work. Gravity is going to be down. The ball will move kind of up and down. And air resistance is kind of like friction here. If the ball is going right, air resistance is going left. So those two are parallel. The work will be done. And again, this will be negative work. So friction is an other force. We don't have a type of potential energy for it, as with air resistance. So this is going to count, if it's doing work, in our work other. So we will have some work other. Work other will not be equal to 0. And these are actually some really common scenarios that you'll see. Roller coasters, work other is 0. Pendulums, work other is 0. So if you see a problem right away where there's a roller coaster or a pendulum, you right away think, okay, work other is going to be 0, which means this equation here is going to be very easy to use. If you see a problem where there's friction or a problem where there's air resistance, we know that work other is not going to be equal to 0. This equation still applies. It's just going to be trickier to use because we're not going to be able to just cross this out and say it's 0. So now I want to do an example with you guys where this work other term is 0 and show you how to use this equation. It can be really, really powerful. So here's my example. A snowboarder starts at rest on a 45-meter hill. So he starts up here, travels down the hill into a gully, and up to the top of a 25-meter hill. Find his speed at the top of the second hill. Now, you'll hopefully recall from our motion unit that whenever we have an object that's starting in one place and moving to another place, it's useful to kind of label our diagram with spots that we call initial and final. Where are you calling your initial and where are you calling your final? We used initial and final a lot when we were doing kinematics because we had VI and VF. But now in this equation, we have KEI and PEI and KEF and PEF. So because we have these I's and these F's, these initial and final points, it's worth labeling them on our diagram. So initial is up here, where the snowboarder was at rest, where he started on the top of the hill. And I'm going to call final down here, the top of the 25-meter hill. And this is where we want to know what his speed is. For starters, though, let's assume there's no friction in this problem. Reason being, we know from up here that when we have friction, work other is not 0, and that equation becomes harder to use. Also, snowboarding is a pretty low friction sport. Compared to a car skidding along the ground, the amount of friction you have between a well-waxed snowboard and some nice slippery snow is pretty minimal. So this is a fair assumption to make. The reason this becomes a good assumption to make is that if we can ignore friction, then the free body diagram of this snowboarder looks a lot like that of this roller coaster. You could pretty much just take out this roller coaster and place a snowboarder in there. You'd have gravity acting down on him. You'd have normal force going this way. That would do no work, so the work other would be 0. Again, the only other force the snowboarder might have that this roller coaster doesn't is a bit of friction going that way. But like I said, snowboarding is a pretty low friction sport, so we're going to ignore that friction. So because work other is 0, that equation that I presented you guys with is going to be really nice to use. So right away, we cross out that work other term, we say this is 0, and we never have to worry about it again for the rest of the problem. Okay, what's my next step going to be? Well, this question doesn't tell me how many joules of this I have, or how many joules of this, or how many joules of this, or how many joules of this. So I don't have numbers I'm going to be able to plug into these directly. But I do have equations for each of these that can help me find them. So I'm going to sub in the equations I have. Potential energy, I know, has the equation mgh. I also know that my initial kinetic energy is going to be 0 because initially he was at rest. Notice my work other term is completely gone. Kinetic energy final, he does have some speed here, so he'll have some. And the formula for that is 1/2 mv squared. And potential energy final, he'll have some of that because he has some height here. And again, the formula for that is mgh. So all I've done in this first step is just subbed in the formulas. mgh for potential energy, 1/2 mv squared for kinetic energy. And if I knew something was 0, I said so, or I crossed it out. Next step, let's sub in some numbers. So little g is 9.8, and the height initially is 45. So you do have to kind of be careful here. We've got 1h on this side and 1h on this side. And these are not the same h. You'll notice that on the left side of my equation are all my initials, and on the right side are all my finals. So this is my initial height on the left side of the equation. This is my final height on the right side of the equation. Some people would call this HI and this HF. So they remember that they're actually different. Okay, so then here I have my little g again. That's 9.8, and my final height is going to be 25. At this point, you may be looking at this equation going, this is going to be tricky. There's the v that I know I'm looking for, right? We're trying to find his speed at the end, v. But I've also got this m hanging around, and I don't know what the snowboarder's mass is. So how am I going to be able to isolate v? Well, here's a little math trick that we use a lot of the time when we're using this equation. Because every single term I have here has an m in it. There's an m, there's an m, there's an m. What I can do is I can divide my entire equation by m. So here's my equation just written out again. And what I'm going to do is I'm going to divide the whole thing, divide both sides by m. Remember, in algebra, I can do whatever I want as long as I do it to both sides. So I'm thinking, dividing this by m would be useful because that m would cancel out, it would be gone. Hey, I can do that. I just got to do it on this side. So if I divide my left side by m, that m gets canceled out. If I divide my right side by m, I'm dividing this guy by m, that'll get canceled out. And I'm dividing this side by m, that'll get canceled out. So because every single term has an m in it, dividing by m is great because they all cancel out. So there's my equation written again without the m's. I probably should have just stopped writing this 0, but it helps to keep track that that was our sort of kinetic energy term. At this point, I'm going to plug some stuff in on my calculator, clean this up. So I'm going to do that on my calculator. And I'm going to do this on my calculator. That brings me to here. Now I'm trying to think, OK, how do I isolate this v? How do I get it all by itself? Well, let's start by moving this 245 to the other side. Then I can do 441 minus 245 on my calculator. Now my v is getting a little bit closer to being isolated. I want to get rid of this 1/2. So I'm going to multiply both sides by 2. 2 times 196 gives me 392. And now the only thing I have left to do to get v all by itself is to take the square root of both sides. And I do that, and I get 19.8 meters per second is the speed. You might be looking at this saying, isn't it plus or minus 19.8? And yes, mathematically it is, but we have to choose whether to use the positive or the negative. And in this sense, since we're looking for a speed, find his speed, there's no such thing as a negative speed. So we know to pick the positive one. If this was velocity that we were looking for, yeah, it could be negative 19.8, meaning it's going backwards or left. So there you have it. That's sort of a quick walkthrough on how to use this equation here to solve conservation of energy problems. And this trick of dividing both sides by m comes in really, really, really handy, as long as this work other term is 0. One thing I'd want to highlight about this approach to solving problems is how powerful it is. If you tried to solve this problem without using conservation of energy, maybe just using kinematics, it would have been really, really hard. In kinematics, we have vector hats on all of our equations. So we need to incorporate the direction he's going. But the direction is changing all the time. Here he'd be going right. Here he'd be going kind of down to the right. Here he'd be going right again. Here he'd be going up and to the right. We'd probably have to involve 2D kinematics and SOHCAHTOA, look at angles all the time, and they'd always be changing. So that's one reason why kinematics would be tricky here, is because kinematics is all about vectors, and the direction of his motion is constantly changing. The other thing is kinematics also has a t in it, a time in most of those equations. We'd probably need to know, or it would be helpful to know, how long it took him to go from here to here. So in this question, we don't have any information on time. And this equation doesn't have any vectors in it. And this is what is so powerful about using the law of conservation of energy in physics, is we don't have to worry about vectors and we don't have to worry about time. So you'll find that this approach, sometimes we'll use it to solve questions that we could have already done with kinematics. But by doing it this way, we don't have to worry about vectors. We don't have to worry about time. We can solve things way, way more quickly with a lot more ease. And it's a very, very powerful equation in that sense.